right. Hi, Zoe. Hi, Wei Xiang. Um, yeah, so I guess Polly can sometimes get a little bit depressed seeing these number of people contracted Omicron on the news. Um, yeah, so guys, let's hang in there and see if we could get this big hurdle through. So I'm talking about the pandemic. Okay, I hope everything will turn out all right. Um, and tomorrow, I hope also the exams for you guys will also turn out all right. Um, I understand that college can be hard, okay, because you all have like millions of things to do, um, billions of friends to make, and trillions of fun to make. Um, but you see, guys, you're doing fine. Okay, you're doing fine. So for the exams tomorrow, just try to be yourself. Okay, I think that's the only way you can be a happy person, right? Um, be yourself. And I guess a big part of studying in college is so that you get to know a little bit more uh, who you are, what you can do, what you would do better, okay, with a certain amount of effort. So it's a period of time you try to discover um, what you can do for life or what you can do to make a living for life in the next 20, 30, or even more years. Okay. Um, you won't be able to be good at every subject. That I know for sure. Okay. So let's take things easy, right? If we are good at it, we are good at it. If we are just okay, so with some subjects, well, it's not bad at all, right? You get to know that that's probably not the thing for you. Okay, just be you, and I'm pretty sure that you'll be very happy trying to be yourself only. All right, so you know what? Let me draw you to the box on the upper right of the screen. You see that, hey, it's already 2/3 through the semester. Okay, great job. We have just 1/3 left. Okay, and tomorrow is the second exam. So the exam is going to be much longer, and some of the questions will be trying to get you to think, okay, deeper, okay, than just knowing the things that are a little bit superficial, right? So in a way, when Polly is writing the exams, the purpose is still that hope that you learn something, okay, going through the exam, all right. And for this week, I think the heavy stuff is coming tomorrow. And for Saturday, you have only one quiz to turn in. Okay, so after the big exam tomorrow, then you can take things a little bit easier the rest of the week. And the first topic, or the first two topics today, are about people, research people, what we are trying to do to improve TCP's performance, or trying to prove certain properties in TCP. Okay. The first is that scientists or network engineers are trying to model, okay, the throughput of TCP. Let's check out this video.
Let's cover two more topics related to TCP, and these are about what the research community is doing trying to improve TCP for the future need. First is about how one improves TCP such that it can support long, fat pipe. Okay? What I meant by long pipe is a TCP connection that has long round trip time. And a fat pipe is that it has high throughput. Okay? And this is what we know. Okay? Sending rate, or the throughput, should equal the window size divided by round trip time. So this is 0.1 second. And the rate should be 10 gigabits per second. So you see the congestion window is essentially the two terms multiplied, and that is 1 gigabits and approximately 110 megabyte. So at the sender side, receiver side, 100 megabyte is required to buffer the packets that are in flight. And this is just to maintain one connection, right? If you have 10 connections, that's already 1 gigabyte of memory. If you have 100 connections, that's gonna probably take all your memory away. This is just one issue. Another issue is this. TCP is actually go back and like. What if you run into a packet loss that is triggered by having 3 duplicate acts? What we do there is we set the window size to half of the window size before a loss event is detected. And you know what? The window size, the number of packets there could be, can be as high as this, because if we divide this by 1500 byte, you get these many packets in flight. So in that case, we'll have to retransmit all the unact packets, okay, and half of the window size here, okay? So that's, 41 and 666 something packets that we need to send. The bandwidth consumption there, right? The amount of bandwidth we might be wasting there is very significant. So TCP, the current design, isn't really ideal to support long fat pipes. And this is actually assuming that there's no packet loss at all, no bit error at all. What if we have error? One will have to derive the TCP throughput model considering loss before one can see how big a problem it is to try to support long fat pipes. So let's try to do some derivation here and see if we can come up with the average TCP throughput, okay, provided the window size, round trip time. The assumption is that let's ignore the slow start, okay? Consider just the condition avoidance operation and assume that there's always data coming in. And the scenario is very simplistic, which is illustrated here. Over time, the changes of the window size is exactly from half of W increase all the way to W, and W is where the loss will always occur, and therefore we drop the window size back down to half W because this is in condition avoidance. When there's a loss, drop to half W. When there's a loss at W, drop to half W. And so it's not hard for you to see what is the average window size? The midpoint here, right? So 3/4 of W. And therefore the throughput is what? The average window size divided by the round trip time, which is this term here. Now, if we plug in, this is the goal throughput, and this is the round trip delay. Now, what is the window size now? Well, it will be this term multiplying each other and multiplying the reverse of 3/4. It's 4/3 now. So this is actually even bigger than the CWND we're calculating there. So with loss, the amount of memory required to store data higher, the amount of unnecessary retransmission also higher. We can go on and on, right? Try to derive a more general model. So let me not go over the exact derivation, just tell you, if the loss probability is L, okay, one can actually come up with the TCP throughput being represented this way. Round trip time here, okay, square root of L here, and the maximum segment size here. Now, if take the same example here, take the same setting there. Packet size being 1500 bytes, round trip time being 100 milliseconds, and the goal throughput 10 gigabits per second. In order to achieve so, the loss rate needs to be as slow as this. 2 multiply 10 to the power of -10. Okay. Now this is a loss rate that's also impossible pretty much on the internet today. Right? So definitely we need new versions of TCP to support very high fat pipes going a long way.
All right, so that's what some of the network engineers are trying to calculate, and so that motivate design of the next generation of TCPs. There are some mechanisms being proposed. So in case you're interested, let me know. I can actually send you pointers to some of the papers people wrote to do long fat pipe TCP. Next is fairness. It's a very interesting topic. Okay, so that's
another major issue is this fairness. Okay, let's talk about fairness at this level first, the TCP fairness. Okay, so what we're talking about here, the goal is to make sure that the K TCP sessions will share the same amount of bandwidth if it go across the same link of bandwidth R. So the eventual share of the sending rate or the throughput should be R divided by K. Okay, so in this scenario, what you're seeing is the router in the middle, the capacity is R, and we have two connections. So connection 1 here should have half of R, and connection 2 here should have the equal amount. So we have two competing TCP sessions, and they're competing for a link with capacity R. So what I'm showing here are the relationship of connection 1 and connection 2's throughput. So one extreme is connection 1 gets the whole R, while connection 2 gets nothing. And this is the other extreme. Connection 2 gets R, while connection 1 gets nothing. The fair point is right here in the middle. Each of them gets half of R. So you see here, the dotted black line is to draw the equal bandwidth share, meaning if the bandwidth of connection 1 and 2 falls on this black line, yeah, they'll be fair to each other. Now, the blue line here is actually illustrating, this is actually the boundary, the capacity of the link. Okay? If the sum of connection 1 and 2 throughput goes beyond the blue line, that means congestion is beginning to occur, packets will begin to drop. Now let's say we start from here. Connection 1 having this much throughput, while connection 2 have very small throughput. As time goes by, okay, we're in congestion avoidance state, so we will continue to do additive increase. Therefore, connection 1's throughput will continue to increase, just like connection 2's throughput will continue to increase. And the characteristic, the value of connection 1 and 2's throughput will fall along this line here with the slope of 1. Now, as it goes beyond the blue line here, this is actually beyond the network capacity, we'll begin to see packet drop. And what we'll see next is what? The two of them reducing the throughput to half of the value here. Okay, so this is connection 2's. Connection 2's throughput drop to half of it. Okay, right down here. Connection 1's throughput drop to half of it, right down here. Okay. So having a loss, decrease the window size by a factor of 2. And that takes us from here down to here. So this is the current throughput of connection 1 and connection 2. Let's move on, right? It will continue to go additive increase as we are in the congestion avoidance state. Crossing the boundary of blue line, drop packet again, and decrease the window size again. Okay, again by factor of 2. So we go down here. So you see, additive increase, multiplicative decrease. Additive increase, you see, the throughput of connection 1 and 2 are actually what? Approaching the equal bandwidth share. So TCP between the connections, the mechanism warrants that they will be fair to each other. So we see between TCP connections, they'll be fair to each other. But what about TCP to UDP? Multimedia applications actually prefer not to use TCP because TCP has this window size mechanism when there's congestion drop it, right? So the rate, sending rate is actually throttled by the congestion control mechanism. So some of the multimedia applications would prefer UDP, and they would send audio video data at high rate, constant rate without really adapting to congestion. So would that be fair? Of course not. And not to mention this, what if you have applications who open up multiple parallel TCP connections, okay, versus other applications who opens one TCP connection at a time to send data? Now consider this case. A link of rate R with 9 existing connections already, right? Then each have R over 9 share of the bandwidth. When there's a new app coming in asking for 1 TCP, that app then will share with 9 existing connections and each get 1/10 of the R. But if the new app comes in and then asks for 9 pair of TCP connections, so that would be what? R dividing by 9 plus 9. And each connection is this much because the new app gets 9 of these, so let's multiply this by 9. New app gets half of R. So a new app designing this way versus a new app designing this way, okay, competing with other existing connections, it's actually hard to make it fair. And you know what? Web browsers these days do this. Okay? They might start parallel connections to fetch one page. Previously, Internet Explorer were very aggressive. Okay, for example, starting 8 parallel connections, 4 parallel connections to try to fetch web objects in a page. But nowadays, the HTTP consortium actually regulates so that they do not overdo this.
All right, so from that video, you hear that TCP connections among themselves over a long time, they'll be fair to each other. Okay, very interesting. No matter where the starting point is, one connection might get higher rate at the beginning, another lower, but gradually they would approach the equal share. But so TCP connections will be fair to each other, but TCP, when it's competing with UDP, it's very likely losing the game of getting higher throughput, because in UDP there's no regulation. You can push as much data as fast as possible. There's another competition that TCP might lose, or another way of exploiting transmission of data such that you don't get fairness among the users. Okay, even though you get fairness among the TCP connections, that is at the application layer. So if a browser, okay, is implemented to start parallel TCP connections over another browser, then you see also there's unfair competition to get web pages using one browser versus another. All right, and that takes us to quiz 29. All right. Yeah, so you see quiz 29 is quite different from the previous year's quiz 29 here. So on quiz 29, to the left, you see, that is the example, right? We just went through in the video. We see that connection 1 and connection 2, the starting rate are very different, but gradually it will converge to equal share, the dotted line. So this other scenario on the right, you see connection 1 start with the low rate, connection 2 start with the high rate. Okay, seemingly the opposite of case 1 on the left. Could you try to draw the change, okay, of the sending rates of connection 1 and 2 over time and see if it converges to equal bandwidth share? All right, so for this, I guess what you can do is to grab a piece of paper or open your notebook, right, and draw. Yeah, so there are x-axis and y-axis. One axis is to represent connection 1's throughput. The other is for connection 2. Okay, and you draw the orange line and the dotted line. And then starting from upper right, regime, how would the throughput of our connection 1 connection 2 converge? All right, so let's give it like 5 minutes. Okay, should be straightforward. The purpose is that you exercise a little bit what we just talked about in the video. Yeah, as I said, this should be quite straightforward. We see already, I think the first is team 1, sorry, team 5, right? So if we start from upper left, right, we grow additive increase linearly to the upper right in parallel to the dotted line. And when we hit the blue, multiplicative decrease trigger. So I think I meant MD as multiplicative decrease. That meant when we increase the window size to that point, we drop. Okay, so we drop. So at this point, so maybe I can blow it up a little bit more here. Yeah, as we grow to the upper right and hitting the blue line, right? So at that point, we need to drop connection 1's rate to half of it. So yeah, I think that's about here, which is the second point that Jiahong has drawn, right? So from the first point to the second point, you pull a straight line, right? And then that represents the multiplicative decrease. And then we grow with the slope 1 additive increase again, right? And then we draw it down, multiplicative decrease, and then the linear increase. Yeah, so as I see from team 5, it seems to be converging, right? And I think team 10, Ke is also showing something similar. So Ke actually drew it even closer and closer to the dotted line in the middle. Similarly, Cai Tong did the same. Okay, I think team 1 also managed to do something similar. But you see, team 1, I'm not quite sure your multiplicative decrease is really proportional. So when it's decreasing, it needs to drop to half of connection 1's rate and half of connection 2's rate. So it might be arguable that you are dropping the connection 1's rate to half of it. I think it's a little bit less. And similarly, right, connection 2's rate is also not quite half of it. All right, so team 1, not very precise. There's a risk there. Points might be deducted. So let's see, team 3, right? At this point, upper right, multiplicative decrease. Yeah, I think Cai Tong's plot is about half connection 2's rate that it is dropping to, and half of connection 1's rate it is dropping to. Yeah, I think same for team 10 and team 5. I think team 1, yeah, that rate is a little bit odd. Multiplicative decrease part. Guan Yu here, team 15. I think in team 15's plot, it's also not exactly half of connection 2's rate that you're dropping to. So it should be a little bit lower, isn't it? Yeah. Okay. So just be careful which point you drop to so that it looks like a multiplicative decrease. Now, of course, you can argue that you are doing like 1/3 or 2/3 multiplicative decrease. Okay, so you multiply the rate to 2/3 of the original rate. Then Guan Yu and Liang Xin's plot will make more sense. Okay, but currently, when we are saying TCP's condition control being multiplicative decrease, we always drop to half of the earlier rate. Wow, okay, Hui Xin's plot, perfect. Because Hui Xin actually draw exactly how high connection 2's rate is, and find the middle point, and determining which point it should drop to. All right, this is perfect. Okay. Yeah, then the grader will have no complaint with a solution like this. Okay, very good. And I see that perfectly. You understand what we're doing there. Very good. All right, and I guess the rest of the teams, you guys get the point. And now let's move to the last bit of TCP. Until now, we talk about TCP's condition control mechanism, right? This TCP's condition control mechanism actually relies on whether there's a packet drop being detected. So this is one of those two approaches we talk about doing condition control. And the one TCP is using is end-to-end based. Okay. There's another one, do you recall? Yeah, it's the in-network, network-assisted approach. There's a version of TCP implemented to support this other approach. It's called the TCP-ECN, but it's never really been used.
That was TCP, taking the end-to-end approach. Let me introduce another mechanism that's called the ECN. It's also defined for TCP/IP for the internet, but it's not really implemented or activated. And it's taking the opposite approach, the network-assisted approach. The ECN mechanism works this way. First of all, in the IP packet header, or network layer header, there's this special field called TOS that stands for type of service. So in that field, two of the bits are assigned for the purpose. They are also called the ECN bits. Okay? So I'm using a green packet here to indicate that that packet header, especially the network layer header, is carrying the ECN bits. They were initialized to 0, that means no congestion, but as the packet travels through the network, running into a busy router like this, the bits will be turned on. And the packet will eventually come and arrive at the receiver of the data. And the network layer here at the receiver is going to see, oh, these two bits are turned on, therefore notifying the transport layer. And at that point, the transport layer of the receiver is going to do this. Receiver is going to send the ECE bit on the packet going back to the data source, like this. Okay, so it's going to be in the ACK packet and the ECE bit being turned on. So this is also called the E flag, okay, in the TCP packet field. Sender there, upon receiving this ECE bit packet, will then send a packet that is then the data packet going back to the receiver. And that packet is a little bit special because there's also a special bit being turned on, the CWR bit. So this is congestion window reduced bit. This is so that the destination here, the receiver of the data here knows that, okay, so my notification here, you indeed received it and reduced the sending rate. Okay, so therefore the receiver of the data does not need to send ECE bit again. Otherwise, the source is going to reduce sending rate again and again. And the E bit and the C bit, the E flag and the C flag are in fact, again, in the TCP packet header. Okay, so along with all these other flags for TCP. And that finally takes us to the summary of the chapter 3. We went through the basic functionalities of transport layer protocols, multiplexing, demultiplexing, reliable data transfer, flow control, and just now, congestion control. And we talk about how UDP and TCP implement these services. Particularly, we spend quite a lot of time here, as well as here. We are now finally ready to leave the network edge. So departing from the transport layer and down to the network layer and into the network core. But the network layer is going to be split into 2 chapters. Chapter 4 is going to be about the data plane, how we forward packets real fast. And chapter 5 is going to be the data plane. So how do we control these paths we select such that the packet will travel and eventually reaching the destination, reaching the receiver.
All right, so that indicates we'll be entering a new chapter. So we'll be going one layer down, right? And there's just one remark Polly would like to say to the TCP-ECN design. You see that, of course, there are packets between the receiver and sender. Receiver sends a packet with the E bit on. Sender acknowledge that with the C bit on. Okay, but you see also that, hey, there's some green datagrams traveling at the lower layer inside the network. And the routers in the network might turn some of the bits on, okay, the ECN bits on, okay. Those green packets are called the datagram. They are packets, but there are packets at the network layer, which is something that we will talk about more in chapter 4. So in that, ECN has 2 bits. The use of these bits, okay, are actually more complicated than what I just showed you. So that 0, 0, and 1, 1 are just very simplified way of saying that, hey, we can have some bits there, okay? When you send data out, they are initialized to some pattern. But as it travels the network where there are routers that are congested, not enough buffer space, okay, then they might turn some of the bit to another pattern to indicate that there are congestion forming in the network. Now, that's start chapter 4. It's actually the chapter that Polly likes the best, okay? It's very interesting, and it talks about the part of the internet that many of you know very little about. Okay, I think you guys know very well about the application stuff when we started talking about application layer protocols. You guys heard about TCP UDP already, and quite oftenly. So you might also know a little bit what's going to happen in chapter 3. But chapter 4, the network layer, it's very unique. Okay, it's very unique. In fact, in chapter 5, which is also a network layer, you will hear about algorithms that you might learn in the algorithm course. Okay, so let's start with chapter 4, which is the easier part of the network layer. And this video is an overview of chapter 4.
Welcome to chapter 4, the network layer, and particularly the data plane. So in this chapter, the goals are understanding the principles behind these network layer protocols. And we'll focus on data plane and talk about the other one, the control plane, in chapter 5. So in the overview section, we're going to talk about the service models possible for these network layer services. And we'll talk about the main functionalities that people implement in the network layer. Forwarding and routing. We'll talk more about these. And we'll be spending some time here talking about the architecture of a router and how packets travel through a router. And the rest of the chapter will be spending a lot more time here talking about forwarding of packets generally, as well as how it's implemented, how it's working on the internet. 4.1, the overview of network layer. Well, what the network layer is doing is simply this: transport segments from the sending host to the receiving host. So let's use the micro internet here as an example. And let's assume this guy here is the sending host, and this guy here is the receiving host. So the goal of the network layer service is so that we could send segments or packets through the internet to the receiving host. Now, what's a bit special though, okay, in the network layer? It's not only the two end hosts have the network layer protocol implemented and operating on the machine. Each and every router inside the network here would also have the network layer protocols running. Now, to be exact, on the sending side, on the sending host here, the transport layer segments is going to be encapsulated into the datagrams. So a packet at the transport layer is called the segment. But when a packet now goes into the network layer, it's called a datagram, and sometimes also called the IP datagram. Okay, so transport layer, TCP layer; network layer, IP layer. Transport layer, we have the TCP segments. Network layer, we have the IP datagrams. Okay, so at the sending side, we encapsulate these transport layer segments into the IP datagrams. Now these grams, datagrams, will go on to the network and travel from router to router. And each of the router will examine something special, okay, in the packet header, in the IP datagram header, okay, and decide where to pass it further on. So that magic we'll talk about more in the sections to come. Finally, when the packet arrives at the receiving side, okay, so this is the receiving host, the network layer is going to look at the datagram, remove the packet header, and pass the segment, okay, up to the transport layer. So that is the lifetime of a packet traveling the network through the network layer. So in animate, so packet coming from above, pending the header, so packet gets a bit bigger, and you see routers busy forwarding the packet and eventually reaching the receiving host. And at the network layer header or the IP datagram header removed and the segment restored and pushed up, okay, to the higher layer. Right, so that is a general picture of what the network layer protocol is doing. Now, the network layer protocol is doing two major functionalities. As you observed earlier, is forwarding. The routers are all busy moving packets around from one router to another router. Hopefully, it gets to the next router that is appropriate so we don't take too much time to pass the packets until it reaches the receiving host. The other is this. Okay, this is also the magic that I was talking about. So this is the computation, the intelligence in the network layer that determines, okay, a route between a pair of sending host and the receiving host. Or a lot of times we just call them the source and the destinations. So to determine an end-to-end path to travel over the internet from the source to the destination. And that intelligence is also called the routing algorithms. An analogy is this. Let's assume the class is taking a trip to canteen. Yeah, I know the weather is getting warm. It will be really nice if we're in canteen. Well, the thing you need to do first is this, routing. You pre-compute or you Google, okay, and come up with a plan, okay, for the day of travel. Whether we take a bus to the Taipei station or we take a metro to the Taipei station. And from the Taipei station, do we take the high-speed rail? And from the high-speed rail station at Kaohsiung, do we take another bus or do we all rent a car or rent a number of these bikes so that we ride along all the way to canteen? Okay, so the computation process, the intelligence that we need to do ahead of the travel is called the routing. Now, on the day of travel, we'll bring this Google map printout saying, hey, you start from home, you walk to a particular station, and you hop on a particular metro line. And once you get to the Taipei station, you just hop onto, high-speed rail number 112. And then after arriving at Kaohsiung, you go to a particular bus stop, and then you hop on the next vehicle taking you to canteen. So that is this forwarding. Okay, so at every interchange point, you look up a piece of paper and find out what is the next step to do. So this way, it ensures that the forwarding part, the traveling part is going to be fast and smooth. So the separation or the differentiation between the routing function and the forwarding function.
All right, and we actually call the forwarding function is for the data plane of network layer. And the routing function is for the control plane of the network layer. So let's hear more about data plane, control plane, these two terms, how they are different.
And that should make it a bit clear for you to see the separation between data plane and the control plane. So by data plane, we actually meant to talk about the forwarding function. And the control plane, on the other hand, is the routing function, the part that is trying to identify a path between the source and the destination. Now let's talk a bit more about the data plane. Okay, so what's being done there is very local. Each router is determining for each incoming datagram who should be the next router to forward it further. Okay. And that is the forwarding function. So it's illustrated here. For a datagram coming in, this router here is looking up a table and find out, oh, this should be the outgoing port and therefore reaching the next router. Now, the control plane, on the other hand, is the part implementing the routing functionality, okay, implementing the intelligence. It is to determine, okay, how would the packets be able to travel end-to-end from the source to the destination. So these routing algorithms will be implemented in the control plane. Now there are two different approaches implementing the control plane. One is the traditional approach. The other is called the SDN approach. Okay. The traditional one is the distributed approach. And the modern one, the SDN one, is actually more centralized. Okay, to your surprise, isn't it? Okay, we are actually moving from distributed solution to centralized solution. Now, in the traditional one, each router will be implementing the routing algorithm, and the routers will also exchange information among themselves. As a result, and collaboratively, they calculate an end-to-end path. Now, in this centralized approach, in the SDN, we actually ask a couple very powerful machines, a couple very powerful SDN servers that are actually sitting far away from the routers to do the computation. And then after computation is done, they're gonna install the routes back into the routers. Okay. So the tables are actually computed on the routers locally in the traditional way. But more recently, the modern way is to have some powerful machines computing all the routes and then install them back to the local routers. And local routers no longer do the complex route computation. So let's talk a bit more about the data plane. So this is the forwarding part. So this is the part implementing the per router action. And it's very simple, very fast. All that is done is the packet coming in. The router look at the specific packet header field and match to an entry in the forwarding table. So this is called the fast output interface lookup. Once we get a match, we get also the outgoing interface. Let me illustrate. So these are the routers. And inside the router, you see this is the entire operating system stack. There's this thing called the forwarding table, and each router will have one of these. When there's a packet coming in like this, it's going to look into a packet header field and matching the pattern here to the entries in the table. Now, we see that this guy is the matching entry. Therefore, immediately we see the packet should go out on interface 2. So output interface 2. So this is the direction to forward the packet further, and therefore next is going to arrive here in this router. So this is exactly the detailed step of packet forwarding in the data plane. And the control plane is here, higher up in the operating system stack. To be more exact, and let's talk about the traditional approach first, where the computation is distributed. So the routing algorithm is going to be running on each of these routers, and up here. Routing algorithm here, 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 and here. So each and every router is going to have the routing algorithms running, and they're going to interact with each other. So there are these exchanges of messages between these routing algorithms distributed on the routers. And this is the control plane. As a result of the computation and exchange, they find out what should be the forwarding table for different incoming packet, for different packets going to different destinations, and install the local forwarding table into the data plane. So this is the separation of the control and the data plane. Now, in the modern days, we take the centralized approach, the SDN approach. Now, it looks a little bit different, the separation of the data and control plane. So routers protocol stack stop right here, because the computation is all where? Up here. A couple machines, powerful machines, doing the computation. But it cannot be computing without information provided by the routers here. So these routers will have a tiny little process running here. They're called the control agent. The control agent here is going to provide input to the remote controller. This is the big process implementing the routing algorithm. So after collecting information about who they are and the connectivity of these routers to other neighboring routers, now this controller here can then do the powerful computation. Once the result is obtained, those tables are communicated back, sent back to the control agent, and therefore installed into the data plane of the routers.
All right, so that was the overview of Chapter 4. And we won't have time for the subsequent videos, so we'll call it a day. And that's all for the day. Feel free to type up if you have any questions. And for the teams who have not yet completed quiz 29, feel free to use the remaining time to try to come up with your solutions. Otherwise, I will see you tomorrow during the exam. So try to come a little bit earlier so that will allow Polly to check your ID a little bit earlier. All right, so with that said, I see you tomorrow. And best of luck as well. Bye. And speaking of canteen, yeah.